Combustion processes. Topics to be covered. In today's session, we will explore several essential topics related to combustion processes. We'll begin with combustion efficiency, defining it and distinguishing it from overall boiler efficiency, particularly focusing on fuel-to-air ratios and heat transfer. Next, we will discuss air levels and their impact on efficiency, including the effects of insufficient and excessive air. We'll examine how exhaust gas temperature affects efficiency and identify common causes of high temperatures, such as soot buildup and poor airflow. Additionally, we will review combustion efficiency testing and the standard measurements taken, including oxygen, carbon dioxide, carbon monoxide, and stack temperature. Finally, we will discuss boiler load efficiency, maintenance practices, and ways to reduce combustion losses. Let's see these topics in detail. Combustion. Combustion is a fundamental chemical process where fuel reacts with oxygen to produce heat and energy. Achieving efficient combustion is critical. It requires a precise fuel-air ratio to maximize energy output while minimizing emissions and fuel waste. This process is vital in systems like boilers, where efficient heat production is essential. Proper control of combustion processes leads to optimal performance and a reduced environmental impact, making it a central focus in energy production. Fuels. Various fuels, including natural gas, oil, and coal, release energy through combustion. Each type of fuel possesses unique properties that influence both efficiency and emissions. The choice of fuel significantly impacts system performance and environmental outcomes. Factors such as energy content, cost, and availability play a role in fuel selection. Therefore, achieving efficient fuel combustion is key to energy savings and effective pollution control. Carbon. Carbon is the primary heat-producing element found in most fuels. When fully combusted, it yields a high energy output and produces carbon dioxide as a byproduct. Efficient carbon combustion not only reduces fuel consumption but also minimizes harmful emissions. However, incomplete combustion can lead to the production of carbon monoxide, a dangerous pollutant. Therefore, managing carbon oxidation is essential for ensuring system efficiency and environmental compliance. Hydrogen. Hydrogen also contributes to the heat produced during combustion, yielding water vapor as a byproduct. While it enhances overall heat output, it increases exhaust humidity. Fuels with high hydrogen content may require adjustments in the combustion process to optimize performance. Efficient hydrogen combustion supports overall energy efficiency, so finding the right balance in hydrogen combustion is crucial for optimal boiler operation. Sulfur. Sulfur content in fuel is a concern as it produces sulfur dioxide when combusted, contributing to acid rain. Managing sulfur emissions is vital for maintaining environmental compliance and ensuring equipment longevity. Using low sulfur fuels can help reduce corrosion and lower maintenance costs. Proper sulfur management not only aids in regulatory compliance but also minimizes harmful environmental effects. Nitrogen. Nitrogen, while generally inert, can form nitrogen oxides, or NOx, at high combustion temperatures. NOx are pollutants that contribute to smog and respiratory issues. To limit NOx formation, it is essential to reduce combustion temperatures. Efficient combustion systems actively manage nitrogen levels to avoid negative environmental impacts. Therefore, balancing temperature and efficiency is key to achieving cleaner combustion outcomes. Chemistry of combustion. The chemistry of combustion involves complex reactions where fuel molecules combine with oxygen, releasing energy in the form of heat. This process typically produces carbon dioxide and water as the main byproducts. Efficient combustion optimizes these reactions to yield maximum energy output. A thorough understanding of combustion chemistry can help improve efficiency and lead to cleaner energy production through precise control over the combustion process. Source of methane. Methane, the primary component of natural gas, is recognized as an efficient fuel for combustion. It burns cleaner than coal or oil, resulting in lower carbon dioxide emissions. Its high energy output makes methane suitable for various applications. By utilizing methane, we can significantly reduce soot and particulate pollution, aligning with environmental goals and supporting cleaner energy initiatives. Complete combustion. Complete combustion occurs when all fuel is fully oxidized, producing maximum heat output with minimal pollutants. This ideal scenario results in the production of only carbon dioxide and water. Achieving complete combustion necessitates sufficient oxygen and a proper fuel-air mixture, which minimizes fuel waste and harmful emissions. Therefore, Ensuring complete combustion is essential for optimal energy use and cleaner operation of combustion systems. Incomplete combustion. Incomplete combustion, where a fuel, example ethane, C2H6, reacts with insufficient oxygen, O2, producing carbon monoxide, CO, water, H2O, and solid carbon, C, instead of the complete combustion products, carbon dioxide, CO2, and water. The reaction shown illustrates how incomplete combustion occurs due to limited oxygen supply, leading to the formation of harmful byproducts like CO, which is a toxic gas, and unburned carbon. This highlights the importance of proper oxygen levels for efficient and clean combustion. Chimney. A chimney is a vital component in combustion processes, serving as an exhaust system for the byproducts of combustion. It provides a controlled pathway for gases, such as carbon dioxide, CO2, carbon monoxide, CO, water vapor, H2O, and unburned hydrocarbons, to safely exit the system and disperse into the atmosphere. Chimneys rely on the natural draft effect, where hot gases rise due to their lower density compared to the surrounding cooler air, facilitating efficient removal of exhaust. Proper chimney design ensures optimal airflow, prevents backflow of harmful gases, and reduces environmental pollution by minimizing incomplete combustion. Additionally, chimneys play a key role in maintaining consistent combustion by supplying fresh air and controlling pressure within the system. Stack temperature sensor. A stack temperature sensor is a critical device in combustion processes used to monitor the temperature of exhaust gases as they exit through the chimney or stack. This measurement is essential for evaluating the efficiency and performance of the combustion system. High stack temperatures often indicate heat loss, suggesting incomplete heat transfer or poor insulation, while unusually low temperatures might signal incomplete combustion, potential condensation of exhaust gases, or blockages. Exhaust gases. Exhaust gases in combustion processes are the byproducts produced when fuel reacts with oxygen. These gases typically consist of a mix of carbon dioxide, CO2, water vapor, H2O, nitrogen, N2, and, depending on the combustion efficiency, traces of oxygen, O2. In cases of incomplete combustion or impurities in the fuel, harmful gases like carbon monoxide, CO, unburned hydrocarbons, and oxides of nitrogen, NOx, and sulfur, SOx, may also be present. Chiller. A chiller is not directly part of combustion processes but plays a complementary role in systems where combustion-generated heat or exhaust gases are utilized for cooling purposes. In such setups, absorption chillers may use heat from combustion to drive a thermodynamic cycle, often in cogeneration or trigeneration systems, where energy efficiency is maximized by producing power, heat, and cooling from a single fuel source. Boiler efficiency. This image explains boiler efficiency by illustrating the energy input, output, and losses in a boiler system. The fuel input, 100%, combines with air and water to generate steam as the main useful output. However, various energy losses reduce the boiler's overall efficiency. Dry flue gas loss, heat lost through hot flue gases exiting the stack without transferring enough energy to the water. Hydrogen loss, H2 energy lost due to water vapor formed by hydrogen combustion. Moisture in fuel, heat loss from evaporating moisture present in the fuel. Moisture in air, energy loss due to heating water vapor present in combustion air. Excess oxygen loss, O2 heat lost when excess air cools the combustion process. Surface loss, heat radiated or conducted through the boiler's surface. Fly ash loss, unburned particles leaving with flue gases. Bottom ash loss, unburned fuel particles remaining as ash in the boiler. To maximize efficiency, these losses must be minimized through proper operation, maintenance, and optimized fuel-air ratios. Boiler efficiency improvements reduce fuel consumption and emissions while increasing output. Condensing boiler. A condensing boiler is a type of boiler that recovers heat from the water vapor in the exhaust gas, which improves its efficiency. How it works. Burner, fuel is burned in the boiler, which heats up water. Waste gas, the hot waste gas passes through a heat exchanger. Heat exchanger, this heat exchanger condenses the water vapor in the waste gas, releasing latent heat. This heat is used to preheat the incoming water. Flue, the remaining waste gas exits the boiler through a flue. Water, the heated water is then circulated to radiators, where it heats the building. The diagram shows the basic components of a condensing boiler. The hot waste gas is passed through a heat exchanger, which condenses the water vapor. This condensation releases heat, which is used to preheat the incoming water. The remaining waste gas exits the boiler through a flue, heat exchanger fouling. Heat exchanger fouling refers to the accumulation of unwanted materials on the surfaces of a heat exchanger during operation. In combustion processes, fouling significantly impacts efficiency, reliability, and operational costs. Understanding the mechanisms of fouling, its effects, and mitigation strategies is crucial for maintaining optimal performance in systems like boilers, process heaters, and power plants. Soot and fire ashes. Soot and fire ashes in combustion processes are byproducts formed during the burning of fuels, particularly in incomplete combustion scenarios. Soot consists of fine carbon particles resulting from unburned hydrocarbons, often appearing as black, powdery deposits. Fire ashes, on the other hand, are the inorganic remnants of fuel combustion, comprising minerals and compounds like silica, calcium oxide, and other trace elements. Both soot and ashes can accumulate on surfaces of combustion equipment, such as boilers and heat exchangers, leading to fouling, reduced heat transfer efficiency, and increased maintenance needs. Thank you for your attention. For more details, please contact TSD Office Engineering. GHG. We appreciate your interest in ESG initiatives.